The Philosophic Corruption of Physics, Lecture 5.
Okay, it's 2 o'clock, so let's start. At the end of the last class, I read to you the fairy tale that today's physicists believe. Now, according to the fairy tale, the physicists who developed quantum theory reluctantly renounced the laws of identity and causality because experimental results forced them to do so. Now, I pointed out that we can know on philosophic grounds that this fairy tale history is wrong. There's no way to reason from observations of specific entities acting in certain definite ways to the conclusion that the entities lack identity and act randomly. Physicists must have rejected identity and causality on philosophic grounds which had nothing to do with the observations. And I mentioned at the end last time that when we look at the actual history, this is exactly what we find. This is confirmed. German physicists emphatically rejected causality before the development of quantum theory. Now, the first version of quantum theory was published in 1925 by Werner Heisenberg. The next year, Erwin Schrödinger published a version of the theory that was essentially equivalent to Heisenberg's, although different in mathematical form. By 1927, the interpretation of the theory had been worked out, primarily by Niels Bohr. Now, Bohr worked at the University of Copenhagen, so the accepted theory became known as the Copenhagen interpretation. And it has remained the officially accepted dogma for the last 70 years. So the theory was worked out between 1925 and 1927. Now let me read you a few typical quotes to show you what German physicists thought of causality in the years prior to quantum theory. The first is from Hermann Weyl, a prominent German physicist who wrote in 1920, quote, "The quantitative relations in the world are approximate, not merely in consequence of the limited precision of my sense organs and measuring instruments, but because they are in themselves afflicted with a sort of vagueness. The rigid pressure of natural causality relaxes, and there remains room for autonomous decisions whose locus I consider to be the elementary quanta of matter." Unquote. Now, elsewhere, he writes that the elementary particles are not material, not extended, and perhaps their essential property is will. Now, here's another quote, one of my personal favorites. Walther Nernst, a Nobel Prize-winning physicist and chemist, wrote in 1921, quote, "The principle of causality as an absolutely rigorous law of nature has laced the mind in Spanish boots, and it is therefore the obligation of research in natural science to loosen these fetters sufficiently so that the free stride of philosophic thought is no longer hindered." Now, how about this one from one of the founders of quantum theory? Schrödinger writes in 1922, now this is still 5 years before Bohr puts the crowning touches on the quantum theory. Schrödinger writes, quote, "The burden of proof falls on those who champion absolute causality, not on those who question it." Elsewhere in the same article, Schrödinger adds, "Chance is the common root of all the rigid conformity to law that has been observed." Unquote. And finally, we have from the official interpreter of the quantum theory, Niels Bohr. In 1922, Bohr writes, quote, "The development of quantum theory requires a final renunciation of the idea of causality and a radical revision of our attitude toward the problem of physical reality." Unquote. Now, there's a famous story about Bohr that illustrates my point here. In 1929, after the development of the theory, Bohr was explaining quantum theory to an old friend. He explained how physicists have been forced to give up the ideas of identity and causality, whereupon his friend exclaimed, "But Niels, you told us all that 20 years ago." Paul Foreman, an historian of science, sums up the situation. Quote, "Quasi-religious conversions to acausality became a common phenomenon in the German physics community during the early 1920s. As if swept up in a great awakening, one physicist after another strode before a general academic audience to renounce the satanic doctrine of causality and to proclaim the glad tidings that physicists are about to release the world from bondage to it." Unquote. Now, Foreman perfectly captures the attitude of German physicists in the 1920s. Unfortunately, he merely describes the situation without offering any intelligible explanation for it. So, what is the explanation? Well, first, notice that something new is going on here. This is different from previous irrational theories in physics. Consider Einstein's theory of relativity, which I argued was based on Kantian subjectivism and rationalism. Now, you might have thought that things couldn't get much worse. But quantum theory is much worse. No comparison. Einstein had accepted Kant's primacy of consciousness, but at least he maintained that the phenomenal world was orderly and lawful. Physicists conceded that they were aware only of a world created by our minds, but to a certain extent they continued to treat that world as if it were real and intelligible. Now, the quantum physicists reject even that. Reason does not rule even within the realm of its own creation. Even the phenomenal world is ruled by chance and is ultimately unintelligible. The previous generation had called Boltzmann the last pillar of classical physics. But the quantum physicists of the 1920s knew that, strictly speaking, that wasn't true. The basic pillar on which all physics rests is not a man, but an idea. The idea is the principle of causality. And this is the idea they set out to demolish in order to bring the edifice of physics crashing down. Why? Well, if you've read the ominous parallels, then you already know the answer. Quantum theory is simply an expression of the nihilism that dominated Germany during this period. Freud's psychoanalysis, Heidegger's existentialism, Hitler's Mein Kampf, and quantum theory all emerged from the same culture within the span of a few years. All have the same basic cause. The proximate cause is nihilism, a metaphysical rage against reason and reality. The ultimate cause is Kant. Kant was the father of nihilism. In metaphysics, he denied reality in order to make room for an illusion. In epistemology, he denied knowledge in order to make room for faith. Those are his words. In morality, he denied happiness in order to make room for duty. Now, I can't possibly find a way to explain this point any better than Dr. Peikoff already has. So, I want to just remind you of a couple of brilliant passages from the epilogue to Opar, which is worth rereading if you haven't read it recently. Quote, "Kant offers humanity no alternative to the realm of that which is, and no reward for renouncing it. He is the first philosopher in history to reject reality, thought, and values, not for the sake of some higher version of them, but for the sake of the rejection. The power in behalf of which his genius speaks is not pure reason, but pure destruction. The result of Kant, in Ayn Rand's words, was hatred of the good for being the good. The hatred took shape in the culture of nihilism. Modernist intellectuals are comparable to a psychopath who murders for kicks. They seek the thrill of the new, and the new to them is the negative. The new is obliteration, obliteration of the essential in every field. They have no interest in anything to take its place. Thus, the uniqueness of the century behind us. Philosophy gleefully rid of system building. Education based on the theory that cognition is harmful. Science boastful of its inability to understand. Art which expelled beauty. Literature which flaunted anti-heroes. Language liberated from syntax, verse free of meter, non-representational painting, atonal music, unconscious psychology, deconstruction and literary criticism, indeterminacy as the new depth in physics, incompleteness as the revelation in mathematics, a void everywhere that was acclaimed by the avant-garde with a metaphysical chuckle. It was the sound of triumph, the triumph of the new anti-ideal, of the unknowable, the unreachable, the unendurable. In a Kantian reality, nothing else was possible. Unquote. Now, that is the explanation for 20th century quantum theory. Nothing less will explain the emergence of quantum theory, and nothing more is needed. Now, the physicists who were primarily responsible for the theory practically quote chapter and verse from Kant's Critique. For a clear and concise statement of Kant's primacy of consciousness, it's hard to beat the following quote from Schrödinger. Matter is an image in our mind. Mind is thus prior to matter. In defending his rejection of causality, Bohr writes, quote, even in the great epic of critical philosophy, and that is Kant's philosophy, there was only question to what extent a priori arguments could be given for the adequacy of causal connection of experience, but never question of inherent limitations of such categories of human thinking, unquote. True enough. When Heisenberg explains his approach to interpreting quantum theory, he simply paraphrases Kant. Recall Kant's words. Hitherto, we have assumed that our knowledge must conform to objects. We now make trial whether we will have more success by assuming that objects must conform to our knowledge. Now, you remember that quote from Lecture 1. Well, compare the following statement of Heisenberg's. Quote, the interpretation of quantum theory was approached by turning around the question. Instead of asking, how can one in the known mathematical scheme express a given experimental situation, the question was put, is it true that only such experimental situations can arise in nature as can be expressed in the mathematical formalism? The assumption that this was true led to limitations in the use of the concepts of classical physics. Unquote. So Heisenberg, a la Kant, denies that mathematical theories must conform to observed facts. Rather, the facts must conform to his mathematical theories. Okay. Well, so far I've told you the essential new idea of quantum theory, the renunciation of causality, and the basic cause of the renunciation, Kantian nihilism. But I haven't told you anything about the physics, and it's time that I did. So let's start into that now. And the first point that I want to talk about is the so-called wave-particle duality. In the 19th century, physicists had proven that light behaves like a wave. Waves have a property that clearly distinguishes them from particles. When a particle combines with another particle, we have a place where there are two particles, that is, twice as much physical stuff. In other words, particles combine by simple addition. Waves, on the other hand, combine in a more complicated way. If a light wave is split into two beams, and the beams are recombined, they can add or subtract from one another. And it isn't difficult to see why. A wave has peaks and dips. Okay, a wave is not localized in space. It exists continuously over a certain area of space with peaks and dips. When two waves combine, if both are peaking or both are dipping, the waves will add to form one wave with a larger amplitude. On the other hand, if one of the waves is peaking while the other is dipping, then the waves will cancel each other, resulting in no wave or at least a smaller wave. Okay, does everybody see that? Now, it had been known for a long time that light had this characteristic property of waves. Two beams could add or subtract when combined. However, in the early 20th century, it was discovered that light also had characteristic properties of a particle. It was shown that light exists in discrete units localized in space called photons. So light seemed to be both a wave and a particle. Furthermore, in the 1920s, physicists discovered that this paradox was not restricted to light. All the elementary constituents of matter exhibit both wave and particle properties. This was actually first put forward by a young French physicist named Louis de Broglie in, I think, 1924. Electrons, which had always been thought of as particles, it was found that in certain experiments they seem to add and subtract like waves. Okay, now how are these results interpreted in quantum theory? Well, very simply. Light, for example, is both a particle and a wave, even though the two models contradict each other. This is the infamous wave-particle duality. The experiments were explained by saying, in effect, that light is a wave when we don't look at it, and a particle when we do. Light travels through the physicist's experimental apparatus and combines with other light in a wave-like manner, and then, in a random act of magic that is by its very nature impossible to describe, the wave turns into a particle at the detector. Now, I'm not making this up. This is the official, almost universally accepted theory. Bohr explained it in terms of his so-called principle of complementarity. According to this principle, it is valid to assign contradictory properties to an entity in order to describe and predict its behavior. But we can never observe the contradictory properties at the same time. So, according to Bohr, there isn't really a contradiction. And if this makes anyone feel uncomfortable, we can avoid the problem by not using harsh terms like contradiction. Instead, Bohr calls the wave and particle models complementary, a word with a soothing and reassuring sound. Now, Bohr's idea of complementarity gave rise to a new field called quantum logic. Some versions of the new logic explicitly dispense with the law of excluded middle, which is considered old-fashioned and overly restrictive. Excuse me? Oh, the law of excluded middle. That is Aristotle's law that everything has to be either A or non-A. But according to quantum logic, it's not true that a thing has to be either A or non-A. It can be both at the same time. Now, how could physicists accept such nonsense? Well, remember what Kant said about reason inevitably falling into contradictions when it tries to understand reality. And then Bohr's ideas don't seem so surprising after all. Now, to convince you that I'm not exaggerating, let me read a few quotes from the horse's mouth. Bohr writes, quote, "There is no quantum world. There is only an abstract quantum description." Okay, remember what Kant said. All there is in physics is a mathematical description of the appearances, right? We're not describing a reality out there. Well, Bohr holds exactly to the Kantian party line. There is no quantum world. There's only an abstract quantum description. Elsewhere, Bohr adds, quote, "Atomic physics deprives of all meaning the well-defined attributes that classical physics would ascribe to the object," unquote. Now, Bohr confesses his motive in the following passage. Quote, it has been my desire to emphasize how profoundly the new knowledge has shaken the foundations underlying the building up of concepts, on which not only classical physics rests, but also all of our ordinary mode of thinking. It is above all to this emancipation that we owe the wonderful progress made during the last generation. Unquote. Now, this is how the quantum physicists view their rejection of physical reality, causality, and logic. It is an emancipation. Now, Bohr was the leading interpreter of the quantum theory, but the other physicists were happy to jump on the bandwagon of irrationalism. Here's what Heisenberg has to say. I apologize for giving so many quotes, but this stuff is so ridiculous that I can't imagine you would even believe me unless I gave the quotes. So here's Heisenberg. Quote, "It is useful to remember that even in the most precise part of science, in mathematics, we cannot avoid using concepts that involve contradictions. Modern physics has perhaps opened the door to a wider outlook on the relationship between the human mind and reality." In other words, an outlook that includes contradictions. Now, both Bohr and Heisenberg were eager to apply the new logic of contradictions to other fields as well. In general, Heisenberg claims that thought and action are complementary. Quote, "The decision to act finally takes place by pushing aside all arguments, both those that have been understood and others that might come up through deliberation, and by cutting off all further pondering. Even the most important decisions in life must always contain this inevitable element of irrationality." Unquote. Now, given this view, it won't surprise you to learn that Heisenberg was sympathetic with the Nazis and cooperated with them when they came to power. Now, philosophically, Schrödinger was no better. Schrödinger writes, quote, "We have been compelled to dismiss the idea that a particle is an individual entity which in principle retains its identity forever. It is beyond doubt that the question of sameness, of identity, really and truly has no meaning." Unquote. Now, were there any prominent physicists who opposed this insane nihilism? Well, there were two. One was Einstein, and we'll get to his views in a few minutes. The other was a young French physicist named Louis de Broglie. I mentioned him earlier. De Broglie actually tried to develop a theory that would explain the apparent wave-particle duality in a physical, causal, non-contradictory way. And he started very logically. In effect, he said, we have evidence for waves, and we have evidence for particles. Therefore, both waves and particles exist. They are not to be collapsed into the same thing, a contradictory wavicle. Now, in order to explain the experimental results, de Broglie proposed that the particles are guided by the waves. In effect, they ride on the waves. He first published this so-called pilot wave theory in 1927. Now, you can imagine the reception his idea received. Just when physicists thought they had rid themselves of reality, causality, intelligibility, here was this upstart Frenchman trying to bring them back. The reaction was hostility. Here is de Broglie's account of the history. Quote, "Having a very realist conception of the physical world, and little given to purely abstract considerations, it was my wish to present the union of waves and particles in a concrete manner. The particle would be a localized object incorporated in the structure of the propagating wave. I was very satisfied with the results I obtained because they seemed to me to pave the way toward a true interpretation of the quantum theory. I freely admit that my article only constituted a first stage and was destined to be subject to modification and improvements. But I hoped that I would be helped in this task. Now that is pitiful naivety. He goes on. But I was faced with redoubtable adversaries. Niels Bohr, Max Born, Pauli, Heisenberg, and Dirac. They abandoned any clear picture of a wave or a particle. I was very distressed. Unquote. Now the result was that de Broglie gave up pursuing his theory for more than 2 decades. Probably because he lacked the certainty that he was right. Maybe because he lacked the courage to fight alone. I regard this as a very sad story in the history of physics. But happily, there is a sequel to the story that I want to mention here. Louis Little, whom I mentioned earlier, has recently resurrected de Broglie's basic idea of pilot waves and modified it in a revolutionary way that I think is very promising. Little's theory, which was published 2 years ago, seems to provide causal explanations for all the alleged paradoxes in quantum physics. Furthermore, he shows that the same physical model that explains quantum theory also explains relativity. Now, that's a very impressive accomplishment. To my knowledge, Little has developed the first real theory of the quantum world. That is, the first theory that can't be vetoed on philosophic grounds. Now, the bad news is that so far, physicists are entirely ignoring the theory. But it's only been 2 years, so there's hope. Okay, now, next I want to describe for you a famous thought experiment that was devised by Schrödinger in 1935. You may have heard of this. It's the Schrödinger's cat paradox. And this Schrödinger's cat paradox is a reductio ad absurdum of quantum theory. Now, the experiment has never been done. It could easily be done, but it would be unnecessarily cruel to the cat. Besides, the statement of the experiment alone proves the absurdity of quantum theory. The actual results wouldn't add anything to the proof. Now, before I describe the thought experiment, I need to clarify something about Schrödinger. I've already given you some Hoare quotes from him. Now, philosophically, his ideas were roughly equivalent to Heisenberg's. Both men were neo-Kantian rationalists who rejected identity and causality. Both thought that our senses give us awareness only of disconnected phenomena, not of reality. Both thought that to the extent that it's proper to speak of reality at all, reality consists of mathematical equations. And yet, strangely enough, Schrödinger rejected the Copenhagen interpretation of quantum theory. Now, Schrödinger himself couldn't explain why he rejected it. In my view, he never gave reasons that explained his rejection of quantum theory. The reasons he gave are so weak, I've decided they aren't worth repeating here. So let me speculate and give you my guess as to why Schrödinger couldn't accept the theory. He didn't oppose it on philosophic grounds, so I think his opposition was in part psychological. He was not as corrupt as Bohr and Heisenberg, so he simply couldn't stomach quantum theory. Years after the development of the theory, Schrödinger said, "I'm sorry I ever had anything to do with it." Now, he couldn't say why he was sorry. He was just sorry. I think this is the only example in history of a scientist winning the Nobel Prize for his work and then openly confessing that he wished he hadn't done it. Okay, now let's look at the cat paradox. Here is Schrodinger's description of the thought experiment. Quote, "A cat is pinned up in a steel chamber, along with the following diabolical device. In a Geiger counter, there is a teeny bit of radioactive substance, so small that perhaps in the course of 1 hour, 1 atom decays, but also with equal probability, perhaps none. If an atom decays, the Geiger counter discharges and through a relay releases a hammer that shatters a small flask of hydrogen cyanide. If one has left this entire system to itself for an hour, one would say that the cat lives if meanwhile no atom has decayed. The first atomic decay would have poisoned it." Unquote. Okay, now I've drawn this on the board partly to show off my artistic ability, but just to give you something to look at here. You see the radioactive sample in the Geiger counter hooked up to the relay such that when the Geiger counter goes off, the hammer drops, breaks the vial of poison, killing the cat. Now, how does quantum theory describe this physical system? Oh, I should mention, it's also crucial to this experiment that this whole apparatus is enclosed in a box that the experimenter cannot see in. Now, how does quantum theory describe this physical system? Well, in the theory, there's no cause for radioactive decay of an atom. The decay happens purely by chance and is described by a probability function. After the box has been closed for an hour, the theory describes a system as an equal mixture of two states, one in which the atom has decayed and the cat is dead, and one in which no atom has decayed and the cat is alive. Now, physicists claim that such a description does not reflect our ignorance of the actual state of the system. It is the actual state. Quantum theory says the cat is in a state of limbo between life and death. It is alive and dead, both and neither at the same time. Everybody get that? What happens when we open the box? The new observation causes the system to collapse into one of two possible states. The cat will always be observed to be either alive or dead. But the unambiguous condition of the cat was allegedly brought about by the observation. Prior to opening the box, the physical system had no identity. It was a mixture of contradictory states. Now again, I am not making this up. I couldn't dream of anything this crazy. My imagination isn't that good. Now here's what one physicist, John Gribben, has to say about this. Quote, "Until we look inside the box, there is a radioactive sample that is both decayed and not decayed. A glass vessel of poison that is neither broken nor unbroken. And a cat that is both dead and alive, neither alive nor dead." Schrodinger thought up the example in order to establish that there was a flaw in the Copenhagen interpretation, since obviously the cat cannot be both alive and dead at the same time. But is this any more obvious than the fact that an electron cannot be both a particle and a wave at the same time? Good point, right? Common sense has already been tested as a guide to quantum reality and found wanting. The one sure thing we can know about the quantum world is not to trust our common sense. Unquote. That is the standard view. Now, let's hear from the founders of quantum theory. Heisenberg writes, quote, "The theory does not allow a description of what happens between observations. Any attempt to find such a description would lead to contradictions. This must mean that the term happens is restricted to the observation." Unquote. Elsewhere, Heisenberg states that the transition from the possible to the actual takes place during the act of observation. In other words, reality itself has no identity. It's in this contradictory mixture of possible states until we observe it. And then it becomes something specific. Phil, you have a question?
Something that, has always bothered me about this, even as a kid, when I heard about this, was what do they consider to be an observation? The cat is looking at it, so does it have to be human consciousness giving rise as an observation?
Phil asks, well, what about the poor cat? Can't he count as an observer? I think that, now that sounds like perhaps a ridiculous question, but it is such a silly situation that this is the kind of question that physicists end up debating. And in fact, there is a debate on this issue. You laugh, but physicists have brought up exactly this point. The cat maybe could cause the collapse of the wave function by observing. Right. It's not a question, of course, that needs an answer. The fact that that question naturally comes up is just further indication of how absurd this whole thing is. Okay, now here's what Bohr has to say about this. Quote, "One can assert with a certain right that the measuring result is produced only by the measurement itself." Unquote. Now, I could say that Bohr and Heisenberg are stealing the concepts of measurement and observation. Obviously, a measurement presupposes a definite something that is measured. But on their view, there is nothing to measure and nothing to observe until the act of measurement, which then creates the property that is measured. But what are we acting on? How do we measure nothing? Now, I have to admit, though, that I'm somewhat embarrassed to even make that criticism, because stating the issue in terms of concept stealing doesn't convey the full magnitude of the absurdity here. One doesn't have to understand the hierarchical nature of concepts in order to see that this theory is utterly ridiculous. A child could see it. Now, as I've said, the standard interpretation of quantum theory is primarily due to Bohr. Philosophically, Bohr was somewhat eclectic, but he is best described as a pragmatist. One of his favorite philosophers was William James. Now, pragmatism is a development from Kant. According to Kant, our minds do not perceive reality, they create it. James and the other pragmatists agree. They just give this idea that we are not spectators, but rather the active creators of reality, a different twist than Kant gave it. Dr. Peikoff writes in The Ominous Parallels, quote, "Reality," the pragmatists state, "is not fixed and complete in itself. It is not ready-made. In reality, it is unfinished, plastic, malleable, indeterminate. In itself, reality is a spread of something without identity, something which is nothing in particular." Unquote. So there are no facts prior to our activity. We create the world of facts by our action. Now, this is exactly the way Bohr interprets the quantum theory. There is really nothing new in Bohr's ideas. They're just a straightforward application of pragmatism to atomic physics. Does everybody see how Bohr's ideas are connected to pragmatism? His basic idea is simply that reality, there's some spread of stuff out there, but it has no identity until we measure it, act on it, observe it, and our act of observation and measurement confers identity on the thing. It becomes something. Now, of course, not all the quantum physicists were pragmatists. Some of them disagreed with the specifics of Bohr's interpretation. Wolfgang Pauli, who made major contributions to quantum theory, is a good example. Pauli was the godson of Ernst Mach and was strongly influenced by positivism. Now, he didn't particularly like Bohr's talk about physical systems existing in a state of limbo in between observations. According to positivism, it's meaningless to even talk about what happens between observations. There are just the observations and the equations. That's it. Talk about anything else is outside the realm of reason and science. Now, the interesting point here is that the philosophic differences between the physicists who developed quantum theory made no difference at all. Not even to them. Bohr preferred his pragmatist interpretation, but he was very tolerant of the positivist view. He didn't even think the differences were worth arguing about. Nearly all of the pragmatists, positivists, existentialists, and neo-Kantians arrived at the same basic conclusions, and therefore they all got along fine. The common ground was down with reality, down with causality, down with reason. The universe is an unintelligible chaos. Choose whatever path you want, so long as it leads to that conclusion. De Broglie incurred the wrath of these physicists because he rejected the conclusion. He thought that reality was real and that reason could grasp it. That was regarded as heresy. Okay. Well, the next story I want to tell you about quantum mechanics is about Einstein. Einstein's fight against the quantum theory. In a letter written in 1924, Einstein writes, quote, "I should not want to abandon strict causality without defending it more strongly than I have so far. I find Bohr's ideas quite intolerable. If we must accept them, I would rather be a cobbler or even an employee in a gaming house than a physicist." Unquote. There's a famous story about an argument between Heisenberg and Einstein in 1926. Heisenberg defended the new quantum theory by claiming that he was simply following Einstein's own philosophy, that only the observations are real. Einstein replied, quote, "Perhaps I did use such philosophy earlier, and also wrote it, but it is nonsense all the same." Unquote. Now, by this time, Einstein has repudiated positivism and Mach's influence on his early thinking. And Einstein is certainly not an avant-garde pragmatist like Bohr. He was an old-fashioned rationalist with neo-Kantian premises. He found the explicit irrationalism of quantum theory repugnant. He was not in the spirit of the new nihilism. In 1935, Einstein proposed his own thought experiment to prove that the Copenhagen interpretation of quantum theory was wrong. The essence of the experiment can be described very simply. There's a particle source that emits correlated pairs of particles. For example, calcium atoms will, under certain circumstances, emit pairs of correlated photons, particles of light. Now, by correlated, I just mean that the properties of the two photons are related, so that knowledge of the properties of one tells you something about the properties of the other. Okay, I've drawn this basic physical system here on the board. So, say this is the particle source, and it could be calcium atoms. Under the right circumstances, they will emit correlated pairs of photons, one which will shoot off in one direction and one shooting off in the opposite direction. and you have instruments on both sides of this particle source to detect these particles as they fly off. Now, Einstein used this type of physical system to attack the quantum theory. He argued that Bohr and Heisenberg must be wrong when they say that the measurements create the reality. In the case of correlated pairs of particles, we can determine a given property of particle 1 without observing, measuring, or acting on it in any way. We can simply measure the corresponding property of particle 2 and then deduce the property of particle 1. Everybody see that? Now, Einstein argues, since we can determine the property without any act of measurement on the particle, the property must be real, independent of our acts of observation. Therefore, quantum theory merely describes the incomplete state of our knowledge, not the full state of the system. Everybody see the reasoning? Okay. Now, faced with this criticism, did Bohr repent and admit the error of his ways? Of course not. Bohr simply answers that Einstein has assumed the independent, autonomous identity of both particles. According to Bohr, quantum theory treats the particles as inseparable parts of the whole system, which is composed of both the particles plus our instruments. By measuring a property of one particle, Bohr claims, the whole system is affected. So Einstein can't say that the deduced property of the other particle existed prior to the measurement. That's a good response to Bohr's argument. Does everybody see what Bohr's response is? It says, well, this whole system is an inseparable whole. And by acting on this particle, you instantaneously change the state of the whole system. Or rather, even in Bohr's words, create the state of the whole system. So you can't say that the property of this particle that you deduce existed before the measurement on the other particle. Now, it was predictable that this argument of Einstein's would fail. Quantum theory can't be refuted in this way. The Copenhagen interpretation of the theory is not based on experimental evidence, and so it cannot be refuted by experimental evidence. Think of it this way. Einstein, like Schrödinger, was attempting to reduce the theory to absurdity. But the quantum theory is invulnerable to such an attempt because it is already explicitly absurd as stated by its advocates. The attitude of Bohr and Heisenberg is like that expressed by Father Tertullian in his defense of religious miracles. They believe it because it is absurd. They have been emancipated from reality and logic. Remember Bohr's famous words. So the approach of Einstein and Schrödinger was doomed from the outset. Now, what is the proper approach to refuting quantum theory? Well, start by identifying the actual issues, which are philosophical. The physics is irrelevant. The refutation of quantum theory is contained in the first chapter of Dr. Peikoff's book, Objectivism, the Philosophy of Ayn Rand. It is the validation of the axioms, the law of causality, the primacy of existence principle. Now, why didn't Einstein take that approach? Well, the answer is obvious. Einstein was on the opposite premises. He accepted Kant's version of the primacy of consciousness. Now, one can see this in the paper where he presents his argument against quantum theory. Einstein offers the following definition of reality. Okay, here's Einstein's definition of reality. Quote, if, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to that quantity. So reality is determined by what we can predict. Bohr and Heisenberg are wrong, says Einstein. They think reality is determined by our observations, that is, by our perceptions. However, the truth is that reality is determined by what we can calculate, that is, not by our perceptions, but by our concepts. The entire debate took for granted the primacy of consciousness. The battle was fought between those who claimed that reality is perceptual appearances and those who claimed that reality is conceptual predictions. And no one came to say that reality is that which is. Shameless paraphrasing. The weakness of Einstein's position is clearly expressed in a note to Max Born, written in 1948, where Einstein writes, quote, "I am well aware that no causality exists in relation to the observable. But in my opinion, one should not conclude from this that the theory, too, has to be based on fundamental laws of statistics. It may be expedient in the end to keep the basis of the theory free from statistical concepts." Unquote. Now, what Einstein is saying here is that he agrees with Hume that causality is not to be found in experience, but he still thinks we should include it in our theories. Now, that is a weak argument. And it shouldn't surprise you after hearing that Einstein lost this battle with Bohr. Okay, now there's one more point worth making about quantum theory before we wrap up this course. In recent years, there have been some interesting developments pertaining to the type of experiments that Einstein proposed to refute the Copenhagen theory. These experiments here where you have a particle source that emits correlated pairs of particles. In 1964, a physicist named John Bell derived a remarkable theorem concerning these experiments. Now, in the derivation of his theorem, Bell makes three so-called assumptions. And I want to lay out these assumptions for you. Number one, Bell assumes identity. In other words, that entities have real properties independent of observation. Number two, Bell assumes a certain corollary of causality, that physical effects propagate by physical means, not instantaneously. So Bell assumed, for example, that Bohr's response to Einstein was wrong, that something happening to particle 2 could not instantaneously affect the state of particle 1. Okay, number 3. This is Bell's third assumption. The properties of a particle on one side of the source do not depend on the state of the instruments on the opposite side. In other words, nothing about the condition, the state of these instruments, say, over on the right side of the particle source, can affect the properties of the particle emitted on the other side. And vice versa, that the instruments on the left side don't affect the properties of the particle on the right side. Okay, now, given these assumptions and an experimental arrangement, Bell derives an upper limit for the statistical correlation between certain properties of emitted particles. Now, experimental results show, in accordance with quantum theory, that the actual correlations violate Bell's theorem. Now, the upshot is that one of Bell's assumptions has to be wrong. In other words, Bell derived a theorem stating an upper limit on the correlations between the properties of these particles. Physicists went out and did the experiments, found that Bell's theorem was violated. They look at the derivation of Bell's theorem, and they identify these three so-called assumptions that Bell made. At least one of them has to be wrong. The first one was identity. The second one was causality. The third one was this assumption that the state of the instruments can affect, is uncorrelated with the properties of these particles. Now, you know what I'm going to ask. You have to give up at least one of these assumptions. Now, which one should we reject? Well, I think if I'm reading you right, you're all inclined to reject number 3. But is there somebody here that said number 1? You're inclined to reject identity.
I think you did this that you're describing, it would make sense to
Oh, you're trying to guess what the physicists will reject. Oh, yeah. Well, you're absolutely right about that. Yeah, this is an odd group that I have in front of me because you chose number 3 to reject. If this were a group of physicists, everybody in the room would reject both 1 and 2 and say that number 3 was unquestionably true. Number 1, identity, is a self-evident axiom. Number 2 is an aspect of causality, which is simply the law of identity applied to action. Premise 3 is in a completely different category. Number 3 would have to be supported by specific scientific evidence. If you're not a physicist, you can't even have an opinion on the truth and falsehood of number 3. The instruments may or may not have an effect on the particles emitted. Who knows? The only way to find out is to do experiments. From the results of the experiments, the only rational conclusion is that premise 3 is false. Now, this is exactly the approach taken by Louis Little. He rejects premise 3. In Little's quantum theory, physical stuff that combines in a wave-like manner travels from the instruments to the particle source, affecting the properties of the emitted particles. Now, the experimental results are explained by Little's theory while accepting as absolutes the laws of identity and causality. Physicists today, as I said, take the exact opposite approach. They look at those 3 assumptions. They say, identity, out. Causality, out. Number 3, self-evident truism. Now, they interpret these experiments that show violations in Bell's theorem as proving once and for all that, quote, reality has been refuted. Long live the void of nihilism, where contradictions exist and physical entities don't. Now, on that note, let me make a few concluding remarks. If this course were longer, I could go on to describe the bizarre irrationalities in contemporary cosmology and particle physics. But it's hard to top the refutation of reality, so it's just as well that we're stopping here. Now, we've seen the devastating effects of Kantian philosophy on physics. In 19th century Germany, we saw physics swing from the Kantian mysticism of the Romantics to the Kantian empiricism of the positivists. Both schools were based on Kant's subjectivism and on his fundamental premise that reason cannot know reality. By the end of the 19th century, a consensus had been reached. Physicists renounced the goal of understanding the physical world and humbly accepted the job of describing the appearances. The immediate result was Einstein's 1905 theory of relativity, in which he rejected any physical explanation for the constant speed of light and focused solely on the mathematical relations of the appearances. The final result was quantum theory, which, in the spirit of Kantian nihilism, explicitly rejected causality. Now, the question I want to raise is, what is required to get physics back on track? And of course, the obvious answer is objectivism. In the distant future, if and when we reach the stage where college graduates have all read and understood Leonard Peikoff's book, Objectivism, the Philosophy of Ayn Rand, the science of physics will be put back on rational foundations. At that point, physicists will shake their heads in amazement when they look back at 20th century physics, which will be considered the most bizarre episode in the history of science. They will understand why it happened, but they will still find it difficult to believe that an entire century could have taken Kant's ideas so seriously. Now, unfortunately, that future is far away. I doubt that many of us will live to see it. Is there a possible shortcut? Could physicists be persuaded to accept more rational interpretations of relativity and quantum theory even prior to the time when Ayn Rand's ideas will dominate university philosophy departments? And let me put this issue in more concrete form. For the sake of argument, let's assume that Louis Little's theory is correct. There's at least one type of experiment for which the predictions of Little's theory differ from the Copenhagen theory. Now let's assume that someone actually does this experiment, and the results confirm Little's theory and contradict the accepted theory. Now, how would physicists react to that news? Well, there's no doubt in my mind that the creators of quantum theory, men like Bohr, Heisenberg, and Pauli, would not have accepted a rational causal theory under any circumstances. They would never have let the facts, quote, lace their minds in Spanish boots, as their colleague Walther Nernst so eloquently put it. But what about the physicists of today? Are they also committed to Kantian irrationalism? Well, I think a few are, particularly some of the theorists who specialize in cosmology and particle physics. However, in general, I would say no. The attitude of physicists today is not the nihilism of 1920s Germany. As Dr. Peikoff pointed out in the epilogue to Opar, Kant is dead as a cultural power. As a consequence, theoretical physics today is drifting on the inertia of ideas accepted earlier in the century. There is not much in the way of a passionate philosophic commitment to those ideas. Most physicists today don't think a lot about philosophy or the conceptual foundations of their science. They accept relativity and quantum theory with a somewhat reluctant shrug because everyone else accepts it. Some are discouraged that the universe seems so unintelligible, but since they have discarded philosophy, they're also helpless to do anything about it. So the question comes down to, could these sleeping physicists be awakened by a rational quantum theory that predicted an experimental result that contradicts the accepted theory? And my answer is, possibly. Of course, it would be difficult to persuade anyone to do the experiment, since physicists have been hypnotized by the dogma of Bohr and Heisenberg. But it's at least possible that physicists could get a wake-up call from within physics prior to the forthcoming objectivist revolution. Now, such a wake-up call would not be sufficient to put physics entirely on rational foundations. For that, nothing less than the objectivist metaphysics and epistemology will do. But it might be enough to convince some physicists to once again start asking questions about the real physical world, rather than merely describing the random behavior of appearances. They might even get excited with the renewed hope that the questions actually have answers. The field of fundamental theoretical physics today is depressing. Recall Einstein's remark that if he had to accept quantum theory, he would rather be a cobbler or an employee in a casino than a physicist. Now, I would take a stronger view and say the same thing about Einstein's own theory of relativity. Physics is an enormously exciting science if your goal is to understand the basic nature of the physical world. But if you're concerned with mathematical descriptions of appearances, it is uninspiring. And if you're concerned with the statistics of appearances, it's boring enough to cause paralysis in most people. And that brings me to my last point in this course. Physicists need to recapture the enthusiasm of the father of their science. Recall that Newton thought of himself as a boy playing on the seashore, excited by the discoveries he made, and especially by the fact that the great ocean of truth lay waiting to be discovered. Physicists need to realize that Newton's seashore is still there waiting for them. In the words familiar to all of us, it's real, it's possible, it's theirs. They turn their backs on it only because Immanuel Kant declared it off limits. When they reject Kant and discover Ayn Rand, the way will be cleared for full access to Newton's great ocean of truth. And that brings this course to a close. Thank you. Well, we still have 7 or 8 minutes for questions. That's amazing. It's the first time I've finished with that much time. Yes? Gene.
Have you had much, or have you had any contact, or any objectives had any contact with Louis Little, and to see how is he philosophically overall?
I don't know Louis Little well. I mean, I've exchanged a few emails with him on issues of physics. But you know, as far as I know, he is an objectivist in the sense that he accepts certainly the basic principles of the objectivist metaphysics and epistemology, and it's very clear from his paper that he accepts the objectivist metaphysics because he throws it right in the reader's face, which I thought was wonderful. I mean, it's so refreshing to hear a physicist in a published paper in a journal say things like, the Copenhagen theory is absurd, reality is real, and actions are caused by the nature of entities. Now, I mean, you wouldn't, unless you're familiar with the sorts of things that 20th century physicists write, you just can hardly imagine how refreshing that is to read. So I'm very impressed with Louis Little's theory. Yes?
Is this current theory, how about this, is it inhibiting innovation at all? Are latest technologies coming up?
Oh, I mean, yes. That's a good question. The question is, are the confusions in 20th century physics stagnating physics and therefore stagnating any technological advancements that might be based on new discoveries in physics that aren't being made now? Absolutely, I think. There's a large amount of very impressive technology that has emerged from what is known in quantum theory. In other words, there's a lot of technological advances that have been made on the basis of simply having the mathematical formalism of quantum theory that we have. Examples would be nuclear power plants and nuclear bombs, which only depend on knowing the probabilities of the nuclear decays and interactions. And you don't have to know the underlying causes in order to design a reactor or a bomb. But here is my evidence that physics, in fact, is stagnating due to these bad ideas. I mean, I gave you reasons within the course as to how this philosophy of appearances acting randomly would stop you from asking any interesting questions. And since you're not thinking about physical matter anymore, You simply have no physical model on which to ask the right questions. The evidence is that in the last 50 years, physics, in my opinion, has made very few fundamental theoretical discoveries. If you compare the last 50 years to, let's say, the 50-year period from 1785 to 1835, that earlier 50-year period, many, many, many more fundamental discoveries in physical science were made than have been made during the last 50 years. And that is true despite the fact that there had to be tens of times fewer physicists back then doing research and 100 times less funding for research in physics back in that earlier period. And yet they made many, many times more crucial fundamental discoveries. So physics definitely is stagnating. Question, Rob.
What would be required in terms of equipment or funding to run Lewis Little's experiment? How difficult that will be to get somebody, talk somebody into providing that?
Well, there is, as I mentioned at the end of the lecture, there is an experiment in which Lewis Little predicts a result that conflicts with what the standard quantum theory predicts. And in fact, the experiment has already, the type of experiment has already been done. And it was done in the early 80s by Alan Aspect and his group. It's not very difficult to do. I think it would cost maybe a few $100,000. But it's not one of these experiments that takes tens of millions of dollars to perform. I mean, it does require some sophisticated technology, but the unfortunate thing about when this experiment was done back in the early 80s was that the parameters that the experimenter picked were such that the effect that Lewis Little predicts goes to zero. If they had just simply picked different parameters or varied certain parameters while they were doing this experiment, in my judgment, they probably would have found this effect that Lewis Little predicts. And the only reason they didn't find it was just dumb bad luck. Brian.
According to Little's theory, is it the case that, say, if some star sends some light to my retina, that something goes back to the star, somehow conditioning the emission of the light in the first place?
Yeah.
Something like that?
Well, that couldn't be. The question is it necessarily, does Lewis Little's theory imply that the light you receive from a star, you had to get first by emitting some ether wave that went to the star and then the light traveled back on that? Well, obviously not, because the star can be hundreds of light years away, and you weren't around to emit those ether waves. But Lewis Little has an explanation for that, in effect, his theory develops a way in which the light particles can transfer from one ether wave to another, which is his way of explaining the kind of effect that you're talking about. Any other questions? Not so much on Lewis Little's theory, because this isn't a seminar on Lewis Little's theory, but anything having to do with the story I told in this course. Yes?
Does the Germans' choice of quantum mechanics have anything to do with the reason they picked heavy water for their bomb experiments as opposed to uranium?
I don't know the specific decisions that they made in developing the bomb. Now they were still working with uranium, right? It was a fission bomb. They were just using the heavy water as a means of slowing down the neutrons to promote the reaction, is my understanding. But the German bomb project, I would actually like to do more reading on, because I think it's an interesting history. And if those of you who have the journals book, there's I think, a fascinating chapter in the book called Top Secret, where Ayn Rand worked on a screenplay about the development of the atomic bomb, and she says some interesting things about the German attempt to develop a bomb and why she believes they never could have gotten it. Yes?
You are working on a PhD, I understand, in this field.
Yes.
Your PhD dissertation at any of these meetings, and what are your chances of actually getting to read it?
Okay, the question is, does my PhD dissertation have to do with the material we talked about in this course? And if so, how in the world could I expect to get a PhD? It's a good question. My PhD dissertation does have to do with the material in this course. My plan is to write a book basically on the story that I told in this course. I mean, filling out, expanding the story, making it fully convincing to a general reader, not pitching it to specialists in physics or specialists in philosophy. And what I'm currently trying to do is talk my dissertation committee into accepting some part of that book as my PhD dissertation. And that I will have to wait and see how that battle progresses. Okay, well, that's all the time we have. So thank you very much.